Alrighty. In our last chapter of this course, we're going to be talking about sequences and series. So this lesson here will be an introduction to that. So lesson 12.1 talks about sequences and series. In this section, we just kind of highlight what a sequence and series is, do some examples. In the next two sections, we get very specific in arithmetic and geometric sequences and series. Alrighty, so a couple of vocabulary words or just terminology you might not be familiar with. An infinite sequence is basically a list or a sequence of numbers in which it never ends, usually denoted with three dots. So that's an infinite. We also have what we call a finite sequence. And this is a sequence in which it does end. There's some type of pattern that's happening, and then it ends with some number, right? We have what we call summation notation, which is this fancy looking E here. Typically, you're left with some type of letter equals 1 all the way up to some other random number for each term in the sequence. And basically what this is, you take a sequence and you add them all up and it gives you some type of total. So this basically looks like this. So it'd be like A1 plus A2 plus so on and so on, all the way up to whatever this number is, and we get a total for that. Now, properties for what we call this as sigma notation. It has three different properties. The first property is if I am adding or subtracting inside. So, for instance, maybe I have a couple of things going on here. I can actually take these two functions and separate them as two different summations. Sometimes that makes it a little bit easier to solve or simplify or make the work a little bit easier. And then also works vice versa. Maybe I have it written like this, and maybe I want to write it out as just one big notation. The second thing is if I have a factor in there, I can actually pull the factor out. So basically, I notice that everything's being multiplied by 2 or something like that. I can actually take it completely out of the notation. Then I can just go find whatever this notation is and then multiply by that factor, and I'd get the same answer. The third thing is kind of an interesting notation, but sometimes, again, can make it a little bit easier to solve. But if I start off with a regular summation notation, I can actually separate this as this type of notation. So I can now go I equals 1 up to K. And then what I can do is I'll take that first term up to K plus 1, all the way up to N. So this is a notation you can use to make it a little bit easier on yourself. I've used it a couple times, but a lot of times that's not my first go-to. All right, we also have summation formulas. So if you see this, you can then instantly just plug it in. So for instance, if I have a summation of a function of 1, then the answer will just be whatever the n is. So like 1 plus 1 plus 1 up to 10 times, that will be the answer. The next one, if I have just a regular I can actually use this formula, which is n times n plus 1 divided by 2, and I would get my summation. And then the formulas from there kind of build off of that. So then I would have n times n plus 1 times 2n plus 1 divided by 6. And then again, just keeps building on and on from there. All right, so those are just some formulas. So if you see these type of terms, you can just plug it in and just work it out. When we do talk about an infinite series, it can do one of two things when you're trying to add them up. The summation is then written as an infinity sign. Again, we're just going to infinitely keep on going. This can either converge or diverge. So this would, if it converges, it will converge to a certain number. But if it diverges, it will equal like plus or minus infinity or something like that. Like, see, they're getting really, really big or really, really small. It's not converging to anything. And then, of course, at the very end, it does talk about the most famous sequencing, which is the Fibonacci sequences. And basically what it does, you start off with a number, then you add that number. So 1 plus itself is just 1. Then I'm going to add the two previous numbers. So 1 plus 1 is 2. Then I'll add those two previous numbers and get 3. Add these two previous numbers and get 5. Add these and get 8. Add these and now get 13. Add these and now get 21, and so on and so on. So this is a famous sequence of events, and we'll kind of work through some of those in the examples. And that's pretty much everything that's in 12.1, just a basic overview of sequences, series, and summations. And in the section, you're really just going to be practicing dealing with that, dealing with sequences and stuff. And then in the next two sections, we'll get more specific on arithmetic and geometric. They actually have like formulas that we can use to develop an equation to find all the terms in the sequence. All right, so the very first thing you're going to be asked to do, you're going to be given a sequence, or an equation for a sequence. So it'll say like an equals 7n minus 3. And you'll be asked to find the first 5 terms of the sequence whose nth term is defined. All right, so all we have to do here is you find the first term. So you're just going to plug 1 in. So 7 times 1 minus 3. So that's 7 minus 3, which is 4. Then I'll do a sub 2. This will be now 7 times 2 minus 3. So that's 14 minus 3, which is 11. Then you do a sub 3. And that would be 7 times 3 minus 3. So that'd be 21 minus 3, which gives you 18. And then a sub 4 will then be 7 times 4 minus 4. Oh, not minus 4 minus 3. So that'd be 28 minus 3, which is 25. And then a sub 5 would be 7 times 5 minus 3. So that'd be 35 minus 3, which is 32. And then there's your first 5 terms. Now, usually after the first 3, you can usually see a pattern. You can see I'm going from 4 to 11 by adding 7 more, adding 7 more, adding 7 more. Once you identify the pattern, you can just keep on going. And just to let you know, once you find the first number, if it's written out here, this is what we call an arithmetic sequence. It will increase by whatever the slope is. So this will go up by 7 each time once you do the first number. You just really need to figure out where does the sequence start, and then you can just add 7. All right, so it's an idea. I mean, you can do the work itself, or you can identify patterns, which is pretty much what this chapter is all about, identifying patterns and getting the answer. All right, Let's do another one. Let's look at number 16 this time. And I don't know if I told you that one. I didn't. This was number 10. Number 16 says a sub n equals negative 1/3 raised to the n minus 1. This is not as clean, but it does kind of deal a little bit with geometric sequencing, which I'll show you the pattern here in a second. All right, so here, a sub 1 would equal negative 1/3 raised to the 1 minus 1. Here, 1 minus 1 is 0, and anything to the 0 is 1. Make sure I wrote that down right. Cool. And then a sub 2 would be negative 1/3 times 2 minus 1. So that'd be negative 1/3 raised to the 1. Anything raised to the 1 is just itself. Then I do a sub 3. So I get negative 1/3 times 3 minus 1. So that'd be negative 1/3 squared. To square it, you just apply to both numbers. So that'd be 1 and then 9th. And again, two negatives make a positive. So then I do a force. So that'd be negative 1/3 times 4 minus 1, which will now be negative 1 cubed. Odd exponent means the answer will stay negative. 3 cubed is 1. 3 cubed is 27. And then you do the last one. This time it's to the 4th, so I know it's going to be even. And then that would be, what's that, 81? All right. So again, when dealing with geometric sequences, this is basically when you have a number here raised to an exponent. You got to plug it in to see where it starts. But then from there, whatever this guy is, that would be the ratio that you're going to multiply by each time. So I'd multiply by negative 1/3 each time. So once I get that first number, I could then just keep on going. Again, trying to identify those patterns. All right, let's look at number 43. Number 43 says a sub 1 equals 1, and a sub n equals n times a to the n minus 1 for all n greater than or equal to 2. It has to say this because you can't find 1 from this one. So typically you have to be given 1, and then you can go from there. So we see a sub 1 is equal to 1. A sub 2, I'll then plug this in. So this will be 2 times a sub 2 minus 1. So this then becomes 2 times a sub 1, which we know is 1. So that's 2 times 1, which will give you 2. And then we do the same thing. So we'll go a sub 3. So we'll say 3 times a sub 3 minus 1, which is 3 times a sub 2. This time we know it's 2. So now it's 3 times 2, which is 6. And then we go a sub 4. So that'd be 4 times a sub 4 minus 1, which gives you 4 a sub 3, which will now be 4 times 6, which will give you 24. And then we do one more. That'd be 5 a sub 5 minus 1, 5 times a sub 4. So this would be 5 times 24. That would be 20, 100, 120. Now notice on this one, once I start with this, I see that I'm just multiplying by this ratio. So I can literally just go, all right, if I want to find the second one, I just multiply by 2. If I want to find the third one, I want to multiply by 3. If I want to find the fourth one, I can multiply by 4, and then 5, and so on, and so on, and so on. Or you can do the math to figure out the process as well. Either way works. All right, let's look at another one. Let's look at number 44. Number 44 says a sub 1 equals negative 1. And then a sub n is equal to negative a sub n minus 1 minus 1. Again, for all things greater than or equal to 2. So I got a sub 1 equals negative 1. So then therefore a sub 2 would be negative a sub 2 minus 1 minus 1. So that would be negative a sub 1 minus 1. So in this case, that would be negative 1 minus 1, which will then be 1 minus 1, which will give you 0. Of course, you could do some of that in your head. I'm totally good with that, just showing you the process there. So then I do a sub 3. So then this would be negative a sub 3 minus 1 minus 1. and then this would be negative a sub 2 minus 1, and this will be negative 0 minus 1, which would just be negative 1. Then I do a sub 4, and I get negative a sub 4 minus 1, minus 1. So this would be negative a sub 3 minus 1. And this would be negative 1 minus 1. And I say I get 1 minus 1, which is 0. Kind of seeing a pattern here. You can then guess what the last one is, or you can, again, work it out. So negative a sub 5 minus 1 minus 1 will give you negative a sub 4 minus 1, and that would just be negative 0 minus 1, which is negative 1. So again, once you identify the pattern, you can guess the rest or continue working them out to prove that your theory is right. All right, so that's the first time set of questions you'll be seeing. Let's look at a different set. Let's look at number 49. All right, we're going to find a possible formula for the general nth term for each sequence. Now, in this first section, you don't know anything about arithmetic or geometric, so you have to kind of guess your way through this. So here we go. So I'm going to do 5, 12, 19, 26, 33. And when I say guess, I truly do mean that. You don't know any formulas, so therefore you just kind of have to kind of work with some numbers to see how they are. I am going to go a little different way with this, and I'm going to kind of show you what you can look for to kind of make your life a little bit easier. If you notice that everything is increasing by the exact same amount throughout the entire process, this is what we would call an arithmetic sequence. And again, we'll learn this in the next section a little bit more in depth. But to write this out, it's simply going to be a sub n equals a sub 1 plus d times n minus 1. Right? And so what I mean by that is this right here would be the first term. This right here would be the difference. And you would leave the same as is. So in this case, a sub 1, it goes like this: a sub 1, a sub 2, a sub 3, a sub 4, a sub 5, and so on and so on. So I see that that's going to be 5 plus my difference, which was 7 times n minus 1. The homework is going to expect you to be able to simplify this. So you would distribute. So it gives me 5 plus 7n minus 5, minus 7. And then I'll combine these like terms, so I get 7n minus 2. Right? And then that would be your a sub n formula. All right, so again, the book doesn't talk about arithmetic sequence yet. It just kind of has you guessing like how to build this. I would stick with the arithmetic sequence if you can see it. There are some that are going to not be like this. So let's look at that. Let's look at number 52. Number 52 is given to you as 1/3, 2/4, 3/5, 4/6, and 5/7. So hopefully you kind of see I'm not adding the same value each time, but there is a pattern going on with the numbers itself. So what we can do is, since I know this is A1, let's do that. So if I know, let's build this first. Let's say A1 is equal to 1/3. The correlation to that is this could just be my n, and then this could be n plus 2, right? That would give me that result. Let's see if it matches the next one. So I do 2/4. I see that would be n, and then this would be n plus 2. Really and truly, once I do it 2 times and the pattern does work, I'll just kind of check. I see that's 3, 4, 5, and then I'm just adding 2 each time. You do want to check them all because sometimes it could be thrown off just a little bit. But once you determine that, then you can know that this right here would be the formula to find any sequence in the series. All right. So again, that's just identifying patterns and kind of working it from there. All right, let's look at number 53. This is 1, 1/4, 1/9, 1/16, and 1/25. So again, I do a sub 1. Let's say I just look at it, I'm like, well, that'll just be n. So then I go a sub 2, And I'm like, I got 1/4. I don't see a correlation, but maybe it's just a 1. And then this would be n squared. So now you go back up here and go, well, if this didn't work out, does what I get for number 2 work out? So I'd say, all right, let's put 1 over there, and let's say that's 1 squared. That would all end up being 1. So yeah, that would work. Let's try this next one though. 1/9. That does look like it would give me the n squared. And I can see that then 16 is squared and 25 is squared. So once I kind of identified that, I can then go this route. So a lot of times the first term might not present exactly what you need, but the second one and the third one could potentially give you something else. And then you just kind of go back, go, all right, this worked for this one. Does it work for the previous ones? There's lots of ways to get 1. There's lots of ways to get 1/4, but does it work for each one? Almost like you're solving a system of equations, but really just kind of guessing some and checking some equations. All right, let's look at a different set of questions. So let's look at number 61. All right, you're going to be having to translate each expanded sum that falls into summation notation and vice versa, and then evaluate the sum. So here we go. All right, that's what you're presented with. To do this in expanded form, you really just got to just plug it in. So I'm going to plug in 1 all the way through 7. So if you want, you could do it like this. So a sub 1 would be 3 times 1 minus 5. So that, ooh, I don't know, I got parentheses there. So that'd be 3 minus 5, which would be -2. Plus, look for a sub 2 now. So that's 3 times 2 minus 5. So that'd be 6 minus 5. So that'd be 1. Plus, do a sub 3. So that'd be 9 minus 5, which would be 4. So I'm going to add 4. So hopefully at this point you're seeing, hey, I'm just adding 3 each time. So I'm going to do that. So my 4th term would be 7. My 5th term would be 10. My 6th term would be 13. And my 7th term would be 16. And the reason I'm going to stop there because the number was 7. So this is your expanded form. And then they just want you to add that up. So you would just type this in the calculator. So that'd be -1. That would be 3, 10, 20, 23, and then 49. Right? So both of these would be the answer. This would be the expanded form, and then this would be the actual summation. All right, let's do quite a bit of these. So let's look at number 62. Number 62 as this right here. All right, so in this case, again, doing an expanded form first. So I would do a sub 1 is equal to -3 times 1 squared, which would be -3 times 1, which would be -3, plus a sub 2. So this would be -3 times 2 squared. So that'd be -3 times 4, which would be -12. And then I'll do a third one. So that'd be -3 times 3 squared, which would be -3 times 9, which would be -27. I'll be honest with you, I thought I saw a pattern, but I'm not seeing an outright pattern. I see that I'm really just going to take the 4th one, square it, and multiply by this coefficient. But other than that, I don't really see a pattern with this. So I'm going to keep going. And maybe you might be. You might be yelling at the screen right now going, hey, it's this. All right, so -3 times 16 is -48. And then the last one here, and that would be -75. Again, so that right there would be your expanded form. When you add it all up, you get -165. And that would be the second part. All right, let's do another one. So I got number 63. This time it gives you the expanded form. Not the complete expanded form, but enough to go off of. So what they want you to do is to write out the sequence. So I need to figure out what is my a sub n. I see I'm going up by 7, and then I'm going up by 19. So that didn't work. I see I'm multiplying by 8, and then I'm multiplying by 8, so that doesn't work. Now, these numbers do look familiar. I bet this is 1 cubed, 2 cubed, 3 cubed. 4 cubed would be 64. 5 cubed is 125. 6 cubed is 36 times 6, which I believe is 216. All right, so in this case, that is my series. So I can write my summation. You'll start off with the I equals 1, because that's what we did. And then this will go up to 6, since that's what this last number would be. And I can see it's just going to be I cubed. All right, so I cubed each one to get those terms. Oh, and then we just got to add those up. So 1 plus 8 plus 27 plus 64 plus 125 plus 216 gives me 441. So there's the series, the summation notation, and then this is the summation answer. Right? So again, just like before, you're just kind of looking at it and seeing, can I identify any patterns? Let's look at number 64. We go 1 plus 4 plus 7 plus dot, 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 plus 22. I see that I'm adding 3 each time, so I do need to determine what this one would be. So that would be 10, 13, 16, 19, and 22. So that'd be 1, 2, 3, 4, 5, 6, 7, 8. So I do know my summation notation would be I equals 1. I forgot. 3, 4, 5, 6, 7, 8. Yep. And so there's that first part there. And so then from there, I just need to figure out what is my pattern. So I'm going to go with, I see that I'm increasing by 3 each time. So I'm going to use my arithmetic series information I showed you earlier, and you'll get more of it tomorrow or tomorrow on the next lesson, whenever you watch it. And so remember, the arithmetic series was a sub 1 plus d times n minus 1. So in this case, that would be 1 plus 3 times n minus 1, which will then be 1 plus 3n minus 2. So that would give me 3n minus 1. So that would be, 3i minus 1 would be the series. So again, you kind of check it. 3 minus 1. Ooh. Hold up. Oh, there it is right there. Okay. 3 times negative 1 is negative 3, not minus 2. So then that gives you negative 2. So 3 minus 2. So again, you can check it. 3 minus 2 is 1. 6 minus 2 is 4. 9 minus 2 is 7, and so on and so on. So we know we have a good formula. And then after that, they just want us to then calculate it. So you do 1 plus 4 plus 7 plus 10, 13, 16, 19, 22, and you get a grand total of 92. All right. So again, using this formula right here, and we'll go more in depth in it in the next section, but it definitely helps if you see the pattern. All right, let's do another one of these. Make sure you have enough examples. Let's look at number 68. So we're given I sub 6, or I equals 6, all the way to 13, and you're given I plus 3 and I minus 10. So again, I need to find 6 through 13. So a sub 6 would be 6 plus 3 times 6 minus 10. So that'd be 9 times negative 4, which will be negative 36. A sub 7 would be 7 plus 3, 7 minus 10. So that would give me 10 times negative 3, which will give me negative 30. A sub 8, that'd be 8 plus 3, 8 minus 10. So that'd give you 11 times negative 2. So that would be negative 22. I was really hoping there was a pattern there, but I do not see it now. Ace of 9 would be 9 plus 3 times 9 minus 10 equals 12 times negative 1. So that'd be negative 12. Ace of 10 would give you 10 plus 3, 10 minus 10. So that'd be 13 times 0, which would be 0. Ace of 11, so that'd be 11 plus 3, 11 minus 1. So this would be 14 times 1, so that would be 14. Ace of 12 would be 12 plus 3, 12 minus 1. So that's 15. I forgot the 10 here. Sorry. 12 minus 10, which would be 2. So that gives you 30. And then the last one, so that'd be 13 plus 3, 13 minus 10. So that'd be 16 times 3, which would be 48. So that would be your series here. So you would do it this. So you do negative 36 plus negative 30 plus negative 22 plus negative 12 plus 0 plus 14 plus 30 plus 48. So that's the expanded form. Equals, when you add all of those up, comes out to negative 8. All righty, so let's look at another type of question you'll see. Let's look at number 71. Number 71 are the set of questions you're asked to find a formula for the nth partial sum S of n of each series. If the series is finite, determine the sum. If the series is infinite, determine if it converges or diverges. And if it converges, determine the sum. All right, so what that means is if you're given something like this with an infinity sign, this is an infinite series. So you got to determine, is this going to converge to a number? If it does, let's figure that out. Or does it diverge? Meaning, is it just getting larger and larger or smaller and smaller, like in a hint that is like going towards negative infinity or infinity? When I say getting smaller or smaller, technically we could converge to 0. So is it going towards infinity or negative infinity is really what I'm asking. All right, so you're given this right here. So on number 71, I plus 3, and then I plus 4. All right, when dealing with fractions, most likely you are not going to be diverging. It's going to be getting smaller and smaller to some value. All right, so the best way to go about doing this is once you kind of determine that you're like, I don't think this is going to diverge to infinity or negative infinity, then we need to develop basically a equation that would find out what our summation would be. All right, so here we go. So again, it doesn't really give you too much to play with in the book, not yet at least, but it does say start off with finding your S of 1. So if I wanted my sum of 1 here, I would say, all right, this is going to be 1, 1 plus 3, and then 1 plus 4. So that would give me 4, and then this would give me 5. So I can see from there, from this one here, I added 3, and then this one I added 4. So that's kind of showing the same thing. So what I can do is, let's say we just do S of 2 next. Let's say I do 1, and then I do 2 plus 3, and then I do 2 plus 4. So I see that that's going to be 1/5 minus 1/6. All right, so I can kind of see somewhat of a pattern here. So what I can do, I think probably the easiest thing to do is go, all right, maybe if I go this route and I combine these as one giant fraction. Oh, but using n because it wants you to use it S of n or something like that. Really, the letter is just how they want it. All right, so to add fractions, what I teach a lot of students in college algebra is the easiest approach here is to do crisscross straight across when it's something this easy. So I'll do n plus 4 times 1 and get n plus 4 minus n plus 3 times 1 and get n plus 3. And then on the bottom, I would get n plus 3 times n plus 4. Now, when I do that, that would give me n minus n, which would cancel out, and 4 minus 3, which would give me 1. So that kind of gives me a formula right there. If I fold that out, I don't know if that's going to get us any further or closer to something. Let's look back at example 6. That's what it tells us to go. Oh, you know what? Let's go this a different route. I'm thinking of arithmetic series when we're talking about summation. So technically, S of 2 would technically be this guy. So, hold on. So that would be this plus 1/4 minus 1/5, because you got to take the S1 and S2 together. So I see when I do that, um, 1/5 and 1/5 would cancel, and I'd be left with negative 1/6 plus 1/4. So then when I do S of 3, this will give me 1, 3 plus 3 minus 3 plus 4. So that'd give me 1/6 minus 1/7 plus the previous stuff. So that'd be negative 1/6 plus 1/4. And when I do that, I see that those cancel. And then again, I'm left with negative 1/7 plus 1/4. All right, so what I'm seeing is no matter what I do, I'm still going to be left with 1/4. So I can tell you my summation would equal 1/4. This is converging to this. The issue that we need to figure out is how in the world do we write this out as an equation? Because I can write it as 1/4. And then, okay, so let's see. This would be the same thing as 1/4 minus n plus 4 right there. And then this right here, would that work? So I do 1/4 minus 1/6 here would be again n plus 4, because that'd be 2. All right, here we go. So this formula works. All right, so once we kind of do this, and you can do it again, you'll notice that 1/7 will cancel and you'll be left with negative 1/8. So it's just getting closer and closer to that 1/4. And then now I have a summation notation. So to add to this, get excited about that circle there. So my S of n, which is what it's looking for, is something like this. So 1/4 minus n plus 4. The issue, though, is on your homework, this is where you want to do the crisscross straight across, because they do want it simplified. So this would give you n plus 4 minus 4, because you do n plus 4 times 1 minus 4 times 1, and then straight across. So that'd be 4 times n plus 4. You'll see that the 4s would cancel. So they want something like this. There you go. And to be honest with you, there's not one way to do all of these. So the next one is going to be kind of a different setup, but we'll kind of go through the same process. But let's definitely do another one. Let's look at number 72. Again, this is another infinite one. So we need to figure out, does this converge or diverge? I told you with fractions, it's definitely going to converge to something. You just got to figure it out. I'm going to let you know this, but I'll show you too. Anytime with exponents, it's definitely going to diverge to either infinity or negative infinity. But you can see this as such. So this would be 2 to the 1 minus 2 to the 1 minus 0. So this would be 2 minus 1, which is 1. S of 2 then would be 2 squared minus 2 to the 2 minus 1. So that'd be 4 minus 2, which would be 2. So then that would be plus 1, which is 3. Then you would do S3. So then that would be 2 to the third minus 2 to the third minus 1. So that would be 8 minus 4, which would be 4 plus 3, which would be 7. So you can see the summation is just getting larger and larger as I go. So this would diverge. But it still wants to figure out what is the equation. So I can see that this would just be n. This would be n plus 2, but it's got to be the same thing. So let's see. When I plugged in this value, 2 minus 1, ooh, okay, 1, 3, 7. Let me do another one. I think I might see something here. So 2 to the fourth minus 2, 4 minus 1. So that would be 16 minus 8. 'Cause I can see somewhat of a pattern going on here. So this would be that'd be 8 plus the 7, so that'd be 15. And if you notice, that's one less, that's one less, that's one less. All right, so this would be let's take 2 to whatever the n is, because that would be 2 to the 1 power would be 2, and then take away 1. 2 to the second power would be 4, then take away 1. There it is. And then 2 to the third power is 8, take away 1. There we go. So there's your, it definitely diverges because it's getting bigger and bigger, but there is your equation. Again, you just kind of have to look at it and just see, can you identify some patterns here? All right, I just got one more left for you. So let's look at number 81. This one says determine the first 5 terms of each generalized Fibonacci sequence. So you're given the first one, and then basically just ask for the next 4. So ace of 1 would equal 4. Well, ace of 2 is equal to 7, so you just got to find 3. But you're given that it's ace of n equals ace of n minus 2 plus ace of n minus 1. So if I want ace of 3, that'd be 3 minus 2, which is 1, 3 minus 1, which is 2. So I'm basically just going to add the 2 previous ones up. So 4 plus 7 gives me 11. If I want ace of 4, that'd be ace of 2 plus ace of 3. So again, just adding the 2 up. And then the pattern will just continue. So this would be 29. And then there you go. So when you're doing Fibonacci sequence, you just add the 2 previous ones before it. Right? And that pretty much concludes an introduction pretty much to sequences and series. The next one we'll talk more specifically about arithmetic. As always, if you ever need any help, just let me know. Until the next video.